This is lesson 8.5, constant rate of change and direct variation. A linear relationship is a relationship that has a straight line graph. The rates of change between any two data points in a linear relationship are the same or constant. This is called a constant rate of change. For example, the graph at the right shows the amount of money in Jen's savings account each week. And we can see from this graph that this is a straight line, which means that this is a linear relationship, and the rate of change between any of the data points along this line will be the same. So if I were to use this point here at 1 week and $20, and then this point here at 4 weeks and $80, the rate of change between those two would be the same as the rate of change between this point and this one up here at 6 weeks and $120. So any graph that's a straight line will have a constant rate of change. So in this case, if we wanted to find the rate of change, it says the rate of change in this graph is constant, and savings account is increasing at a rate of blank per week. So we'd find the rate of change just like we did in lesson 8.4. We would choose two data points, so let's use this one and this one, and we'll just calculate the rate of change. So the change in the amount of savings, it goes from $20 up to $80, so that's 80 minus 20. And then over the change in weeks, so from 1 week to 4 weeks, that's 4 minus 1. And 80 minus 20 is 60. 4 minus 1 is 3. 60 divided by 3 is 20. So Jen's savings account is increasing at a rate of $20 per week. Alright, recall from lesson 6.4 that two quantities are proportional if they have a constant ratio or rate. That is, the ratio of each non-zero y value compared to the corresponding x value is the same. The linear relationship in the example above is also proportional. This is an example of a direct variation. The graph of a direct variation always passes through the origin and represents a proportional linear relationship. Okay, there's a lot of information in that paragraph. So what that's saying, if you remember in lesson 6.4, one of the things that we did, and we didn't do this from a graph, but we did do this from a table. One of the things we did to see if something was proportional or non-proportional was to check the ratios of each of the data values. So if you think about these 3 points being listed in a table instead of graphed on this graph, what we would be checking is to see if 20 divided by 1 is the same as 80 divided by 4, and also the same as 120 divided by 6. And that's what we did from a table, but you can also do that from a graph. So let's check that. We did 20 divided by 1. That would equal 20. So this point has a ratio of 20. Here we have 80 and 4. So 80 divided by 4. That's also 20. So that's looking very promising. And then the last data point on the graph, 120 and 6. So 120. 120 divided by 6 is also 20. And if you recall again from lesson 6.4, when all 3 of these ratios, or however many data values there are, when all of those ratios are the same, we would say that this is a proportional relationship. So in this case, we could say that this linear relationship is proportional, and that also makes it a direct variation. We would say that the amount of savings varies directly with the number of weeks. All that means is that as the number of weeks increases, the amount of savings increases. And because a direct variation has to pass through the origin, the additional thing about that is if I extended this line, it would go through the origin here. That means that for 0 weeks, the amount of the savings is $0. So direct variations have to start at 0 as well. They have to go through the origin. Alright, so let's look at an example of a direct or of a possible direct variation. Example 1 says, find the constant rate of change for the linear function at the right and interpret its meaning. Then determine whether a proportional linear relationship exists between the two quantities. Explain your reasoning. Okay, so let's first find the constant rate of change for the linear function at the right. And remember, we know that the rate of change is constant because it's a straight line graph. So let's choose 2 points on this graph to find the rate of change. And let's use this point here and that point there. Okay, so the rate of change between these two, and remember, you can use whatever points you want. The rate of change between these two, let's see, the price increases from $2 to $8. So that's 8 minus 2. And the pounds increase from 1 to 4. So that would be 4 minus 1. 8 minus 2 is 6. 4 minus 1 is 3. And 6 divided by 3 is 2. So we found the constant rate of change for this function is 2. And to interpret its meaning, that means that the price of rice is increasing because we have a positive rate of change. It's increasing at a rate of $2 per pound. Okay, so we found the constant rate of change, we interpreted its meaning, now we need to determine whether a proportional linear relationship exists between the two quantities. So let's check a few of these points to make sure that we get a proportional relationship. So there's 4 points that I've labeled on this graph. Let's check each of those. At 1 pound, the price is $2. So 2 divided by 1 is 2. At 2 pounds, the price is $4. So 4 divided by 2 is also 2. Looking pretty good so far. 3 pounds, the price is $6. 6 divided by 3 is 2. And at 4 pounds, the price is $8. 8 divided by 4 is also 2. So we would say yes. It says to determine whether a proportional linear relationship exists. We would say yes. And the reasoning is because the ratio of price to pounds is the same for all pairs of values. Okay. The try it yourself problem is very similar. You're going to find the constant rate of change, describe what it means, and then determine if there is a proportional linear relationship between the two quantities. So go ahead and pause the video and work through the try it yourself problem. When you're ready to check your work, go ahead and hit play to resume. Okay, for this one, the rate of change is 2.5. And the interpretation there should have been that the plant is growing at a rate of 2.5 inches per week. It's 2.5 inches per week. And then when you check to see if there was a proportional relationship, you should have gotten different ratios at some of these data points. So this is not proportional. And that's because the ratio, unlike in the example one, where the ratio was the same for all pairs of values, in this case the ratio is different for each pair of values. So that makes it not a proportional linear relationship, or not a direct variation. Alright, So flip to the back page and let's go ahead and talk about a little bit more about direct variation. So in this graph, you see three different examples of direct variations. And there are some things we can notice about this graph. First of all, if you look at the similarity in each of the three equations, note that the equations for direct variations are always of the form y equals kx, where k is not equal to 0. So here y equals negative 3x. This one y equals 2x. This one y equals, and we know there's a 1 there even though it's not written, 1x. So this k here will take on various numbers. Everything except for 0 is fine. But that's always what a direct variation equation will look like. Y equals some number times x. In that equation, y equals kx, k is called the constant of variation or the constant of proportionality. And we did see this term in lesson 6.4 also, but it's been a while since we've used that. But that is the constant of proportionality. That's the same value. I'm going to go back a page. That's the same value that we found in this one here to make sure that the relationship was proportional. Same thing here where we found 2 for each of these to make sure it was proportional. And the same thing you checked here and found out that it wasn't actually proportional. So here, that constant of proportionality, that's what we actually found to make sure that the relationship was proportional. I'm missing something here. This should say the equation can be written as k equals y over x. Not sure what happened to that, but that should say k equals y over x. And if you look at the equation, all you're doing to get that is dividing both sides by x to get y over x equals k, which is the same as this. So that just rewriting it that way allows you to see that x and y vary in such a way that they have a constant ratio k. This says that no matter what y and x are, y divided by x will always equal k. This ratio will be the same for any corresponding values of y and x. Okay, so let's see what we can do with that information. Let's look at example 2. As it is being dug, the depth of a hole for a backyard pond is recorded in a table. The first part asks us to write an equation that relates time and hole depth. Okay. And if we quickly check these with our calculator to make sure that this actually is a proportional relationship, when you divide each of these pairs, you should see that you get the exact same number for each one. So we know it's proportional. So then we know, since that makes it a direct variation, we know the equation will look like this, y equals kx. Well, any single one of these pairs of values will fit into this equation. So we can use whichever one we want to figure out what the k will be. So let's use the smallest numbers. That seems the easiest. So we'll replace x with 10 and replace y with 8. So x is 10, y is 8. And we want to solve this for k. So to get k by itself, we want to divide both sides by 10. And 8 divided by 10 is 0.8. Alright, so then the equation is y equals kx, where k is 0.8. So y equals 0.8 x. And that is the equation that relates time and hole depth. Okay. Part B asks us to use that equation to predict how long it will take to dig a depth of 36 inches. Now we have to be careful here to make sure we know whether that 36 represents x or y. This says depth of 36 inches, and I see depth in inches is y. So I know that this value here, this 36, represents y in this equation. So let's take the equation from part A, y equals 0.8x. And this is basically telling me to replace y with 36. So in place of y, we'll put 36. And we're predicting how long. What we're solving for here is x, which is minutes. That should answer the question of how long. So we'll divide both sides by 0.8. And 36 divided by 0.8 is 45. So predicts how long it will take. It will take approximately 45 minutes. Okay. Example 2a, try it yourself 2a, is similar to example 2. The only difference is here you have graph instead of a table. But remember, they represent the same thing. Whether you have ordered pairs listed in the table, like in example 2, or displayed on a graph like this, it's still the same thing. So go ahead and work through example, or try it yourself 2a. Pause the video, work through that. When you're ready to check your answer, hit play to resume. Okay, for this one, you've actually got the exact same equation, or you should have, as in example 2. So you still end up with the equation y equals 0.8x. Pure coincidence, by the way. And then for part B, predict how much 5 pounds of apples would cost. And for this, you should have gotten $4. If for some reason you did not get $4, my guess would be that you replaced the wrong variable with 5. Make sure you're paying attention to what it's telling you. 5 pounds of apples. The weight in pounds is the x value. So if you substituted this for y, you got something other than $4. That's probably what the problem was. So this 5 pounds here, if pounds is x, that 5 pounds needs to replace x in the equation.